Setting up the YouTube live stream. Okay. I think we're live on YouTube. Setting up the YouTube live stream. I'll close that. We'll give it maybe a minute. All right. So thanks everybody for coming to what is actually Black and Astro's first panel all about careers in instrumentation. So really excited to chat about this today. I'm going to introduce our lovely panelists soon, but first I'm going to introduce myself. My name is Keyshawn Ivory. I am the events co-director of Black and Astro. I'm also a third-year PhD candidate in astrophysics at Vanderbilt University. And so now I'm going to introduce our panelists. We can start with Dr. Brittany Miles. So Dr. Brittany Miles characterizes the atmospheres of brown dwarfs and directly imaged planets to understand their chemical composition and cloud properties. She works on detectors to push the sensitivity of instruments to directly image Earth-like planets. Dr. Miles got her bachelor's at UCLA and completed a master's and PhD at UC Santa Cruz. Next, we have Dr. Christopher Moore. Dr. Moore is currently at the Harvard-Smithsonian Center for Astrophysics, holding a dual appointment with the Smithsonian Astrophysical Observatory and Harvard College Observatory. His current science research focuses on the solar corona, specifically working on techniques to improve constraints on the plasma temperature distribution, elemental abundances, and deriving connections between magnetic and radiative fluxes. Chris utilizes X-ray and extreme ultraviolet observations, compares them to models, and works to develop new instrumentation for better measurements. His current instrumentation research includes working to develop new soft X-ray spectrometers for future sounding rockets, CubeSat, SmallSat, and large satellite missions. Chris received his PhD in December 2017, a 2017 IAU PhD prize winner, by the way, from the University of Colorado at Boulder in the Astrophysical and Planetary Sciences Department. His dissertation research included NASA Space Technology Research Fellowship project to help create high reflective coatings for the next gen of astronomical space telescopes, and detector characterization and solar science analysis of the mini X-ray solar spectrometer CubeSat mission. Chris's general research interests include the solar-stellar connection and optical properties of materials. And then finally, we have Dr. Jason Williams. Jason was born and raised in Queens, New York, where he developed a love for Arizona iced tea, dollar pizzas, and the Knicks. He received a bachelor's in applied physics from Columbia in 2016, and recently graduated with his PhD from the University of Southern California. There, he was in residence at Carnegie Observatories, where he worked with Nicholas Konadaris to develop a new high-precision exo-atmosphere spectrograph for the SWOPE telescope named Henrietta. He is now a Carnegie postdoctoral fellow, where he will continue to work on the assembly and commissioning of Henrietta. Awesome. So that's our panel. And I'm going to get us going with just a nice intro question. Can everybody just tell us what kind of instrument do you work on? Give us the specs, tell us the scientific use cases, tell us all about it. Any order.
Say Dr. Miles should go first.
Okay. When we talk about instruments, it's typically associated with a telescope, but what I work on is a little more lower level than that. We're talking about the detectors that we use to capture the relevant light to make our observations. And so at Santa Cruz, a lot of my work was doing more lab-based tabletop characterization of detectors. And as a postdoc, I've changed institutions. I'm hoping to look for a use case on the LBT to figure out what kind of detector or what type of new detector do we need to make the best observation of the planets. And so the science case I'm looking at is, measuring things like ammonia, silicate clouds, and brown dwarfs and planets that we can't see from the ground right now, and also maybe detecting Earth-like planets from the GMT.
I can go next. Maybe the other end of sort of what Brittany is working on is, so she was mentioning instruments as sort of part of a telescope, and so I can sort of show you maybe what she means by that. So let me try and share my screen here. So I'm building an instrument that's going to go on the back of the telescope. I don't know if you guys can see my screen or not. But so basically, the telescope sort of is vertical to here, and the instrument sits on this back plane here. So the telescope is just to collect all the light, and then you put an instrument on the back that sort of fits in this volume here, and then do whatever science the instrument is meant to do. So there's currently an instrument on there right now, what you're sort of seeing here in yellow and silver. The instruments come in all sorts of shapes and sizes. Mine is a pretty large instrument. Sort of looks like this. It's in the testing facility, in our vendor's testing facility right now. So it's like pretty large. It's like close to 500, 600 pounds. And so this will sit on the back of the telescope. And basically what it's designed to do is to take high precision photometry or spectrophotometry of exoplanet atmospheres. So it's designed in such a way that it influences the flux measurement. The instrument influences the flux measurement as little as possible. And so what I mean by that is basically when you look at flux, when you look at light from distant stars, the instrument can change the amount of flux that is recorded by these detectors. And so you basically want to make sure that the instrument influences as little of the measurement as possible. And so that's sort of what Henrietta is designed to do. And this is sort of what it looks like. And I'm happy to field any questions about it. I'll stop sharing my screen.
So here at the Harvard-Smithsonian Center for Astrophysics, I mostly focus on the atmosphere of stars, the dynamics of the coronae. So these are lower mass stars, the masses of the sun are less. But for right now, we particularly focus on the sun because it's so close to us. And this is an example of why. Right here, we have a solar eclipse where the visible light disk is fully occulted, and we can see light being scattered off the free electrons because the gas is so high. It's over 1 million degrees in Kelvin. And hence, these free electrons that are no longer bound to their atoms are free to move around and follow the magnetic field structure. And so they are a great proxy for probing the magnetic field morphology. But not just the magnetic field structure itself. This magnetic field has a large-scale magnetic field structure here, which we call dipolar, and then there are closed field lines near the equator of the sun. That's invisible light. Now, if we look in ultraviolet light and X-ray light, the sun looks very, very different. And here I just want to show a video and credit all to Miloslav Druckmuller. He has tremendous videos of the sun. So these are actual satellite observations. This is not a simulation. It's a composite of 3 different channels in the ultraviolet, where the hottest plasma is probed in the white color, and the purple is the cooler plasma, and the coolest plasma is the reddish black. And what you just saw was the magnetic field rearranging itself, releasing plasma, jettisoning it out into space as a solar flare with a coronal mass ejection, and some of the cooler plasma falling back into the solar atmosphere. So in my summer internship, which I'll talk about later, I saw a video like this and I was amazed and astonished. And I said, wow, if our boring looking sun, which is a plain type star, can have this dynamic effects happening, what are other stars in the universe doing? I can't wait to image those in the future. But of course, like I said, right now, they're so far away. The sun is so close, we can see these dynamics up close and personal. So back to your question, Keyshawn, what are the main drivers for our investigations here in our research group? It's mostly to focus on the dynamics of the solar corona, particularly what are the heating mechanisms that drive the different features and phenomena like solar flares. But also, if you look at this video, which is looping again, you'll see structure almost everywhere and different size scales. And there are variations that happen on different time scales. So I'm mostly focused on what's causing the hot plasma to sit here quiescently always, what's driving these eruptions, and how is that energy transferred out into space via radiation, particles being accelerated, waves propagating, etc. So how do we do that? I'll jump around to a slide to show you guys the general research program that we're building here. As mentioned before, you see the cool videos, but we couldn't see those observations if the technology was not developed appropriately. Dr. Miles Brittany, she spoke about this earlier, focusing on the component level. So we have a portion of our research program which focuses on developing high-speed direct imaging detectors. We take this instrumentation along with mirrors, which I won't speak too much about today, but we work on X-ray telescope mirrors. We put them to spaceflight, verify them on sounding rockets, with the goal of flying them eventually on small satellites and a large satellite. I've worked on CubeSats during my PhD dissertation work, which I'll talk about later, but we combine this with data modeling of the atmosphere with the physics models that are driven by numerical simulations, and we compare those with our observations. And so what we focused on right now, we're focused on the SWIFT Solar Activity X-ray Imager. This is the baseline for a small sat mission, but we are spaceflight verifying it right now in a rocket with a grant from NASA, the low-cost access to space in the heliophysics division. This is scheduled to launch next year in April 2024 to look at a solar flare. But right now we have a team that's actively testing out these optics. We have assembled them into this tube, and we're focusing on the detector right now with our engineering group. And eventually we'll do full instrument characterization in the X-rays. So this is directly imaging X-rays from the sun. And we want to spectrally separate the photon flux and histogram that to get spatial spectra eventually. But for this opportunity, we're just going to focus and collect all the light and integrate it and look for dynamical changes over time and contrast intensity variation. So differences in brightness. Right now, there's a problem with detectors saturating and blooming. Our newer detectors should not have that issue. Here's an example of one of the X-ray grazing incidence mirrors here. There are shells, and they're created from these mandrels. So the mandrels are fabricated, they're polished. These are nickel formed, and then they're pulled off of these mandrels. And then we polish them and then put them into our tube. So that's the main project that we're working on right now. There are many other components and grants that are funded all of these individual components, which we can talk about later. But that's the main driver. What's going on in the atmosphere of these stars, particularly the sun, what's driving the hot plasma for quiescent times, and also these big eruptions like solar flares.
That's awesome. There's so many use cases from the stellar to the planetary. So we got a nice smattering of the different instruments and use cases. Very cool. So next, I actually want to hear a little bit about how each one of you got into instrumentation. Just how did you what was your journey into the work that you're doing now? What got you interested? How'd you kind of like find your next steps? I'd love to hear that.
So I just, my journey in instrumentation started in grad school, but there was a lot of like baggage from undergrad that hindered me from kind of starting really earlier than I could have. So I went to undergrad at UCLA, which is home to the infrared laboratory. And I always felt like, I wasn't like genius enough to do instrumentation. But by the time I got to graduate school, I had a few mentors where I felt safe around to ask questions. And I'm like, okay, I see instrumentation as a way to have agency towards answering the scientific questions you want. And I want to try to understand some component of a bigger like telescope, which is detectors. And so the wavelength I study is in the infrared. It's a lot, the wavelengths are a lot longer than what you see with your eyes, but it's a very powerful regime because it's sensitive to a lot of molecules that are in the atmospheres of planets. And so the limiting factor of that wavelength range is typically the detectors. in the sky background. And so I just wanted to learn more about detector, do something a little more self-contained. And that's how I got into it. And I actually really enjoyed encountering and overcoming problems in the lab. And I felt happy in that space.
Yeah, sort of. So my journey into instrumentation it sort of more so started in undergrad. I always knew that I liked working like in a lab and with my hands, but I didn't have so many opportunities to do that until sort of the later half of my undergrad career. So sort of before that, I I knew a lot. I had some software skills, so I joined a lab my sophomore year, doing primarily like software stuff. Um, and I thought it was interesting, but I knew that's not what I wanted to do for long term. And I still wasn't sure if I wanted to do research or not. Go to grad school, and then I got the opportunity to join an instrumentation lab in my junior year or my sophomore summer. And yeah, I really decided I really liked that sort of thing, and then realized I wanted to do research. I took a year off, still in the same after I graduated undergrad, just really understand if I really wanted to do research or not, and then made the decision I could see myself doing this long term. And then a similar thing happened actually when I got into grad school. I thought I was going to be working on hardware when I got to grad school. Was just working on software for the first 2 years. Really, it was like fine. It was interesting, but I wasn't really what I wanted to do. And then decided to pivot. At the end of my second year, I was like, well, either I'm gonna do what I want to do, or I'm just gonna leave grad school altogether. Got super lucky, found a really good opportunity at Carnegie to work on instrumentation. And then yeah, I've just sort of been doing what I really enjoyed ever since, which is like building instruments and being in the lab, problem solving. And so yeah, so that's sort of been my journey.
So my journey's it's been a pretty windy road. It has not been straight from the beginning. I never really thought about going to college growing up, but fortunately I had the opportunity to go. Majored in astronomy, and while majoring in astronomy as an undergrad, it was suggested to me that I also take physics, many physics courses, so double major. And while taking physics courses, I realized that, man, physics describes almost everything that we see happens in the world that we see. And so that just intrigued me. But at the end of the day, I was still unsure about what I could do with the skill sets with astronomy and even physics when I graduated with a bachelor's. I had an opportunity after my second year, sophomore year, to do an internship at the Laboratory for Atmospheric and Space Physics in Boulder, Colorado. And there, my project was data analysis of satellite measurements, but they had a couple cool labs where you could see instruments being tested and fabricated. So fabricated and also tested, and then being launched. And it was amazing to me that I could actually see these instruments that would soon be orbiting Earth, taking observations of Earth and the sun. And fortunately for me, 2 years later, I had an internship at NASA Goddard Space Flight Center, working on an X-ray instrument for the sun called RESI, the Reuben-Ramity High Energy Solar Spectroscopic Imager. But it was not a traditional type of instrument. It has these big germanium semiconductor detectors. It does something called Fourier imaging. It doesn't directly, quote unquote, image the light. It actually looks at a pattern of probabilities of where the light could have come from in the field of view, and then it's back projected or mapped there. In a statistical sense, one can then reconstruct images of every individual photon event, creating an image. And to me, that just blew my mind. Like, I thought, oh, you just put a lens or you put a mirror and then you focus the light, but there's all these complex ways of detecting the light. And then with that, these detectors were different. So similar to what Brittany was talking about, the detector is like the main aspect of the telescope system, the astronomical light collecting instrument. If you don't have a quality detector, if you do not understand it well, your data is garbage, right? There's all these instrumental effects that could be there that you don't realize are from the instrument itself and not actually from the scientific object you're trying to investigate. And that happened to me in my summer internship, the second one at Colorado. So when I went to NASA to go work on the instrument RESI to do data analysis, there were all these effects. And I'm like, this is crazy. Like, if I was working on this on my own, without help of the science team for the RESI instrument, I'd be lost. And so they taught me how to analyze the Fourier patterns that were created by the RESI observations. And I'm like, this is crazy. I want to learn more about the detectors. So I had an opportunity to go back to NASA Goddard the following summer. This is after I graduated, in between the year of receiving my bachelor's and first year PhD program. And I got a chance to work in the detector systems branch. And so I had an opportunity to dress in the bunny suit and actually work on the micro fabrication for some of the detectors. And so I just wanted to show myself right here in the detector systems branch in the bunny suit at NASA Goddard. And so that was a great experience for me. I did that twice. I learned a lot. I worked on bolometers. I worked on metallic magnetic calorimeters. So these superconducting type of sensors. And I learned a lot of physics. And so it was instrumental for me on my trajectory. And I had an opportunity as a NASA Space Technology Research Fellow that Keyshawn mentioned earlier to go to JPL and to work in the micro devices lab, but for optics. But this further ingrained my interest in working on instrumentation and working on the component level. And so I had a great opportunity for my dissertation research, which I'll talk about a little bit later, to work on CubeSats. And particularly, I was given the opportunity to work on the miniature X-ray solar spectrometer CubeSats. These things are fairly small. This is a 3U CubeSat with 3 cubes stacked vertically. We have 3 of these satellites. I worked directly on 2 of them, and I helped out tangentially on the 3rd. And there's a picture of me holding it. So it's pretty small, pretty fragile. And I learned a lot in that opportunity. I was a detector scientist, so I helped design and modify aspects of the detector and characterize it, calibrate it, data reduction. And we also had a ground station at the University of Colorado to directly communicate with the satellite. So I worked on ground station communications also. But all those things was like, wow, this is really cool. A great opportunity to work on the components, the instruments, and then eventually the satellite. And as we know in astronomy, the majority of astronomy is basically driven by observations. If we don't have the telescopes to collect the light and focus the light, if we don't have the detectors, and now with gravitational waves, if we don't have those type of detectors, there's not much to investigate. You can come up with any theory you want with your numerical simulations that we have, but if we can't corroborate it with any observations, there's not much there.
I'm seeing lots of sort of common themes of, in some cases, starting in one area, realizing that you don't want to do something, and then kind of like winding to where you do want to go. And that's why I really wanted to ask that question, because I know there's probably maybe people watching who might be interested in instrumentation and don't exactly know like where to go next or how to get into it. So I wanted to ask that question. But for my next question, I actually kind of want to contextualize the fields that you work in a little bit more. So I would love to hear in each of your own opinions, what is kind of the state of your field? What are like the big sort of hot button issues, the frontiers, like what is going on in the field that you work in?
So that's a deep question, because you could say the state of the art is whatever came out in the decadal survey, but we know that JWST was made as a galactic mission and we use it for exoplanets a lot. And so, but I think for exoplanet science and like gas giant, like Jupiter-like planets, people are trying to actually get down to those little details that'll help us not just detect an Earth-like planet, but actually say, is it habitable or not? And so I think that is the big question on how we're going to approach it as a community. There's 2 different approaches. So some of you have heard about the Habitable Worlds Observatory. So that's more of an optical mission. And so the challenge with that is if you read materials from this mission, they'll describe it as like contrast, how sensitive you are to certain planets. In the optical, you need to get a contrast of 10 to the negative 10, which is very small and limited by aberrations in the actual instrument in space. And you need to do a lot of work with coronagraphs to achieve that. And so that's the direction NASA has taken. On my side of things, I think there's a lot of work with ground-based telescopes, which have an advantage with angular separation. So with bigger you cannot put a 30-meter telescope in space because it's a big payload. So you have larger telescopes on the ground to look for things very close to the star. And so a lot of ground-based instruments that are coming up on the TMT or the GMT or the EELTs are likely probably some combination of optical and infrared. But I think the big question is, with the data we're trying to get, what can you actually learn about those planets that are habitable? I think that if we're looking for Earth 2.0 and spending a lot of time on it, that's putting all our eggs in one basket. I think the big question is understanding, based on the atmosphere of the planet, can you actually understand planetary formation? How much of an outlier is our solar system compared to the planets we actually see from TESS, from Kepler, and all the information we have on the ground? So that's kind of the big question. And it's not just something we solve with technology. You need observations, which was mentioned earlier.
Yeah, I think from my perspective, or from my perspective of my field is so I mostly work on transiting exoplanets, and I think one of the big questions that we're trying to answer is, okay, well, we have maybe a popular method of detecting exoplanets, which is this transit method, and so we've detected about 4,000 of them so far by this method. And we've detected far more than we have been able to characterize. And the primary reason for that is because the signal. So the primary way that we'd like to detect or characterize these planets is through the atmospheres, and the signal that is imparted by the atmosphere is a lot smaller than it is to detect the planet itself. So we've just detected thousands of exoplanets via the transit method, but have comparatively characterized only hundreds, or maybe less than 200 via the we've characterized the atmospheres of less than 200. So a lot of the work we're trying to do now is, okay, what is the best method to get down to the sensitivity to detect these really small changes due to the atmosphere. And there are a bunch of different ways people are trying to do it. Some people are trying to build survey spectrographs that'll just maybe not get down to the fundamental limits of precision, but will just survey as many exoplanets as possible. Some people are trying to just focus on a handful of exoplanets, and let's just characterize maybe 10 or 15 exoplanets across a wide distribution of parameters. And so maybe we can't, characterize hundreds of these, but we can characterize maybe 15 that have all different sorts of masses and temperatures and radii. Maybe we can get a better understanding of the atmospheres this way. And then some people are, sort of like Brittany said, are trying to get down to the really nitty gritty and saying, okay, what do we know about the detectors? What do we know about the software analysis? And what is really the limits of precision that we can get down to? And so I guess, yeah, that's sort of how I've been seeing my field. There's no consensus on the best possible avenue to take. So I guess we're sort of trying multiple different things. And I guess when it comes to my research, I am sort of in the camp of a hybrid between trying to get down to the nitty-gritty, what is the fundamental limits that we can do from the ground, and also trying to examine as many exoplanets as we can. So sort of doing this in a routine way. So yeah.
So here at the CFA, Center for Astrophysics, we have a a National Science Foundation sponsored summer internship program called the Solar Physics REU. And almost every summer, most of the students come and they say, "You guys study the sun? I thought we knew everything about the sun." And I say, "Yeah, I used to think that too, until I saw, the videos and stuff I showed you all earlier." But that's actually far from the truth. The sun is so close, and you would think we would know everything, but we don't. So I'll talk about a couple of things here. One is primarily, like I mentioned before, the outer atmosphere is orders of magnitude hotter than the surface of the sun, which we call the photosphere. And it looks pretty boring and pale. But essentially, there are two main drivers. One is the actual fluid motions in the photosphere in the surface, driven by what's called convection. Instability in the plasma, you have hotter plasma lower down, it flows up and it cools and loses energy, in this case via motions and radiation. And then the plasma cools and falls back down. That churning motion modifies the magnetic field structure, which allows some of this energy to propagate up into the higher layers of the atmosphere. And somehow, though we're not 100% sure on, this energy is then cascaded down to smaller and smaller scales. Most people invoke turbulence, but how that turbulence is invoked is a nuance that we don't fully understand. So with that being said, I'm showing you images in the X-rays of the sun over time. And in the top, there's one phenomena that we see all the time through the 11-year solar cycle, which are these strong concentrations of magnetic field, which have more X-rays and more UV, which is why they're brighter. They come and they emerge from the surface of the sun, and then they migrate towards the equator. We have an understanding about why that happens, but the fact that these features emerge, we're not fully sure as 100% on how they go about emerging and why does the cycle start and end exactly. That's one big question. The second question is, why is the atmosphere so hot? Against why are we seeing X-rays from the sun in the outer atmosphere? Why is the atmosphere hotter here than the surface? It's number two. But we do understand that the fluid motions in the surface of the sun do give enough energy, and that's what these numbers here are here, the energy flux in these regions, to heat up the atmosphere of the corona. What I mostly focus on, in addition to these, what we call active regions, these bright X-ray concentrations, is like, what are the fundamental processes, like disturbances of magnetic fields, like alpha waves or small transient events, which we call nanoflare heating or micro heating. Are those persistent enough and consistent enough across the surface of the sun? Are they ubiquitous enough to drive the general temperature distribution that we see that's consistent even when these active regions are not present, number one? And then number two, what's driving the active regions themselves? So that's what I mostly focus on. To do that, this is basically the state of the art in terms of spatial sensitivity, in terms of contrast, and also spatial resolution in terms of the fineness of the features one can observe. This is from the Hinode X-ray telescope, which I'm a member of the team here at the CFA. These images are integrated across the entire X-ray band that the Hinode X-ray telescope is sensitive to. So there's a lot of information on the plasma diagnostics, like elemental composition, temperature structure that we can derive from the radiation spectrum that is lost. And so one of the things that we're focused on are creating spatial, spectral X-ray images of the sun at the highest spatial resolution with the highest contrast and intensity and fairly high time cadence to look at the dynamics of these eruptive and ever-changing phenomena. What I'm focused on here to the left, if you can see my cursor, I don't know if you can see it, but there's a couple of bright points that you see that are everywhere. These are small transient heating events, and we're not fully sure what are driving those, but it could be small scale magnetic field rearrangements that liberate plasma and release energy, which then cools via radiation and conduction, and it can change the elemental composition locally. So those are some of the diagnostics and probes that we're looking to directly investigate with our new instrumentation that we currently do not have access to.
Awesome. Wow. A lot going on. Amazing. Well, I wanted to ask that question because I kind of live on for me, like the computational side of things. So I don't get to hear a ton about what's going on in like each of your fields. And so I figured that'd be a really, really interesting question to ask. And also I saw a raised hand. So if you do have a question, feel free to drop it in the Q&A because there will be an audience Q&A at the end. So for my next question, I want to kind of keep going along this line of contextualizing the field. And I want to ask, is there anything that you would want people, and especially other scientists or other astronomers, to know about instrumentation in general or about your area of instrumentation?
I think not enough instrumentation people talk with theorists. I would think that's my at least that's what I have seen reading some of the papers and what people come up with, like requirements and things like that. Sometimes I struggle with this question because it's always the issue of like, what can we do in the next couple of years maybe to do an impact? And can you actually predict what's useful in like 5, 10, 20 years? But I feel like you need to talk with a larger range of people. So I guess I should add more context. There are some instruments that are more facility workhorse that generically the community can use. And there's some projects that are maybe geared towards one question. And so I think it's important to understand what's the most amount of questions you can ask or with your one instrument with X amount of dollars, rather than just saying, I want to do this. And we pick a few things out of a hat on a cycle for the NSF or something like that. So I'm in the process where I'm trying to figure out what's most impactful, and I'm trying to reflect on those questions a little bit more.
Yeah, I think I'd echo a lot of what Brittany just said. Sort of at Carnegie, we do things in a pretty much exactly how she said. There are every decade or so, 5, 10 years, people, there's either a petition for or a proposal for a workhorse instrument, and so an instrument that pretty much most scientists or staff scientists at the institution would use. Or there's a petition for a more specific type of instrument. And the biggest thing that the thing that I think that's done really well at Carnegie is that there aren't a ton of people who do instrumentation, but the people who do instrumentation are like very well incorporated into the community. So there's a lot of feedback with the scientists there, sort of live updates on okay, what is everybody working on? What are the pressing questions in the field? So instrumentalists have a really good idea often of what people are doing, and so we can tailor our interests to, or our designs to what the cutting edge of the field is. And so one other thing I'd like people to know about instrumentation, I think, is that it takes a long time to build an instrument. So two of the most active instruments we're building at Carnegie is my instrument Henrietta, and another one called Miramos, which is going to go on a 6.5 meter telescope. And so my instrument was sort of conceived in late 2020, and we had the plan. It's going to go on a smaller telescope. So typically, smaller telescope, you can build it faster. There's less optics, less issues with mounting the telescope, mounting all the optics. So it typically is done on a faster time scale. Like I've seen instruments of my size being completed in almost 2 years. And so we started thinking about it heavily in the middle of 2020, end of 2020. And we're slated to be on Sky late this year, early next year. So just like things, the pandemic was obviously a huge a huge a roadblock for us. And then cost of things, just general labor shortages, things like that. So yeah, instrumentation tends to take a really long time. And so and I don't think that's particularly kind to the people who are looking to rise up and maybe, let's say, like write a lot of papers, because most of the instrumentalists I know, if that's the sole thing they focus on, don't write a lot of papers, again, because it takes so long to build the instrument. And so then maybe when you're applying for a postdoc or a faculty position or an industry job, you may not have any papers out. So it just may look like you did nothing for 5, 6 years or whatever it is. And so you have to be kind of deliberate in the work that you put out there, and like game planning with your advisor to have like slides and photos ready, so that you can show to people that hey, I actually have been working on a ton of stuff these last few years. And so yeah, that's probably the biggest thing that I think is important for people to know about instrumentation.
Ishan, could you repeat the question for me?
Yeah, so it was just, is there anything that you would want people, but especially other scientists, other astronomers to know about instrumentation, either in general or your specific area of instrumentation?
Yeah, what would I want other scientists to know, astronomers to know, is that instrumentation is very important. My experience, grad school, postdoc, and even parts of undergrad is that there tends to be a notion out there sometimes that the data just comes down from the sky magically and shows up on people's laptops and computers. And that there's a whole entire team that have put in a lot of hours, many years, engineers, technicians, scientists, administrators, et cetera, to design, build, test, launch, operate, process the data that appears on most data analysis scientists' computers. It's a whole team and it's a lot of work. And that's the one thing that I want to make sure that people understand. And that also the data itself is not the truth per se. It is a probing of a system within the confines and limitations of that instrument. And there's always uncertainties. And that it's best if scientists incorporate those uncertainties in the nuances of the instrument itself. And that's supposed to be taken care of by the data analysis pipeline and that team. But yeah, those are some of the things I think I wish more people understood in our field. I think with JWST, it's coming to light more so, and it's back on people's consciousness of the complexities of an instrument, just thinking about everything that had to go into JWST in terms of it launching and unfolding and taking high quality data. It really highlights all of the things that could go wrong that have not gone wrong, which again, I commend the team on JWST for making that happen. But that's what I think.
Dr. Miles, you have a raised hand.
Yeah, I just wanted to comment more about the one about JWST and what Jason brought up about the issue of like productivity and perception in academia. And so like, I think sometimes, I think it's department dependent, but I think more value on instrumentation skills and focus it needs to be like, there needs to be a more holistic approach to what's valuable in astronomy right now. And I don't think we really have that because, I don't think I have publications, but no one probably cares that I know what germanium looks like in a lab off battered zinc selenide or what's going to disintegrate under cryogenic temperatures. Like that's not captured at all the way we measure scientists. And then, things do take a long time. Like JWST, some of the first scientific papers came out 2023, 2022, but some of those reports, I was in middle school, there are actual postdocs and graduate students that dedicated their careers to it and don't necessarily reap the benefits of that work. And so I know like the public has this perception of scientists as like in this altruistic field just for knowledge for its sake, but we're still bound to the whole grind culture a bit and to get things done, which is, yeah.
So I like that you brought that up, and kind of maybe going along those lines, my next couple of questions were going to be about challenges that you faced in the field, both like in a technical sense, but also in like a personal sense. So I guess more directly along the lines of what Dr. Miles just said, what would each of you describe as maybe the biggest challenge you faced kind of life-wise moving through this particular field?
I just spoke, so maybe we can switch it up a bit. So
Yeah, I think for me, I think because instrumentation, again, like I was mentioning earlier, we were all mentioning it takes a long time. You really want to make sure you're in an environment where you're supported, right? And so I think the biggest challenge for me was initially I was mentioning when I first came to grad school, I wanted to work on instrumentation, didn't get that opportunity, but also sort of in the background, there was not a ton of support, right? So I think just a little more background. I think if I were to, if I were to stay with that initial group, and I were to have a hardware project, and actually I know some students who were in that group who were working on hardware, and there wasn't a ton of support. And I think a PhD is very difficult for a whole host of reasons. But I think particularly in instrumentation, you can be drawn out an extra year or two. And so I think the support is, very, very critical. And so I think that is like that. That was my biggest challenge was so after not realizing I would get that support. Okay, this is something I really want to do. How do I find the support that I need? So it wasn't just sort of okay, I'm let go from this group. Finding another group. It took 6-7 months of sort of like a lot of self-reflection on sort of what I want, who are the people I want to surround myself with, and then being sort of okay with if I don't find that, can I will I just be okay with like sort of giving up on this dream of mine? So it was sort of a lot more of an internal struggle, and then just being willing to be patient and be patient for the right opportunity. And so yeah.
So I guess it's my turn, right? So what's the question again, Keyshawn? Just to make sure I answer your specific question.
Yeah. So we're talking about what would you describe as the biggest challenge that you faced as far as like in life, not necessarily technically or scientifically, but in life pursuing this field?
In life, that's a deep answer, but I'll keep it. I'll give one basic one that can translate to everyone, and it's mostly like work-life balance. So in my PhD program, you have to do a comprehensive exam number 2, but it's basically like a master's thesis. For my master's thesis, I worked on numerical simulations. So I worked on magnetoconvection of the solar photosphere. But basically, because I set up the system in the supercomputers, I could just run some code, have some scripts, and it can calculate, and I can go off and do a bunch of things and come back the next day and see what happened. If there's an error in the code and how it runs, the computer just stops, essentially. There's nothing that's really damaged. In instrumentation, as we all know, there's equipment. Many times we're dealing with high voltage, we're dealing with optics, we're dealing with things that could break, they can damage, they can hurt people. If it's done appropriately, one could remotely control your apparatus, your experimental setup. But there are times when high volts are there's water, cooling water or something else. You don't not want to leave that alone. So it sometimes demands a presence, and it depends on the type of test that must be conducted or type of testing that must happen, that you must be present or someone must be present. So you're kind of always involved per se. That leads to this work-life balance and being highly disciplined, highly focused, and like efficient in your scheduling and our scheduling. And that's something I had to deal with as a challenge. That's kind of different for instrumentation versus other type of PhD projects or research projects. Something else to piggyback off Dr. Williams, the timeline. It can take some time between conception of an idea, starting the project, buying and procuring all the equipment, assembling it, seeing something's wrong, buying something else to replace the thing that broke because it doesn't fit, and then doing the experiment or testing, and then writing the paper. That's not necessarily always the case in other type of PhD programs or PhD projects like data analysis or theory, but that's a big difference. I know some people, it took them 6, 7, and even 8 years to complete their dissertation because they had an instrumentation project and a handful of things went wrong or something blew up or something broke. I was fortunate I was 6 years, but that doesn't mean that's the standard for everyone. And I had a couple of setbacks where I had a rocket, that instrument that I was working on for my dissertation. It didn't blow up, but it got cut down, so no observations were made. Fortunately, we had a second rocket launch and I was able to get data. And then thirdly, was able to have my instrument also on a CubeSat, which took data. So that was fortunate. Some people's CubeSats did not work. Some people's rockets with their CubeSats blew up. So I was fortunate in that regard. So those are things that we have to think about as an instrumentalist in general, but also for the dissertation. It's best to have a backup plan, a data analysis project or a theory project to marry with the instrument project, especially if you have to have it take data and operate for your dissertation.
Yeah, I think having patience is probably the biggest thing I had to learn being in instrumentation. So I also had, it took me, for infrared detectors, you have to cool them down. You have to cool them down to really low temperatures because everything in the room emits heat, even yourself. So you don't want that heat interfering with your detector. And so I needed to cool this detector to like 7 Kelvin or something. So I needed liquid helium because we couldn't afford a cryo cooler. I couldn't even get that liquid helium for about a year. And about that time, I had already graduated. And by the time I got it back in Santa Cruz, the experiment didn't even work. So I had to figure out how to continue some of that work at Arizona, even though I put a lot of effort in making the setup work at Santa Cruz. And so everything had worked fine for that project up until that point, until that last test. So it was frustrating, but honestly, sometimes things are not in your control. And I think probably the biggest life challenge, I mean, there's many. Also, the pandemic happened while I was in grad school, and that was like a hot mess. But probably the worst thing I had to encounter was dealing with health issues the same year I was applying for postdocs. So typically before you get your PhD, you have to apply for jobs and then you have to defend your thesis and do all that stuff. So because COVID had happened, I hadn't been to a doctor in a while, but I noticed in lab, my vision was like deteriorating a bit. Like I would see tube or something and my eyes would just get tired. And so basically I had to go through a whole circus of getting adequate healthcare, figuring out it wasn't an issue with my eyes, it was an issue with my brain, and then getting a craniotomy like in the fall of my last year of grad school. And then I was like 28 or 27. So I thought, oh, it's not a big deal. I'm like not old, so it's gonna be fine. But no, once someone goes in your brain, it's like, it's a big deal. So I really had to learn how to just kind of sit still and just be, because I would get headaches and stuff looking at the computer. The brain surgery affected my vision, and I ended up having to get eye surgery again, before moving to my postdoc. And it was just I could be stubborn, but it was definitely a challenge in just like letting myself be and recover. Cause in the moment I was just so mad. I'm like, why am I not doing my work? I could do my thesis stuff, but no, I have to be kind to myself and realize your vision changed 3 times in the last year. Like you got to chill a bit. And if I just have to kind of take care of myself, so that's kind of the biggest lesson from last year. So yeah, it was kind of a hot mess. And then the day right after I published, I think the same time we got early release science observations with JWST, I had eye surgery. I was like, y'all, this is either happening or it's not. Like my eye gonna be at the doctor's table. Like we just gotta let it happen. So I guess now I'm trying to be more for myself and not my job all the time.
Thank you for sharing that. I really appreciate those reminders that we bring our entire selves into whatever the work is that we're doing, and so that means looking after our entire selves. I think that's a really important thing to remember. So before we move on to Q&A, I do have one last question. I think it's an important one because, as I mentioned earlier, I am on the computational side of things, so it's not always obvious to me what someone would do if they wanted to get into instrumentation. So I want to kick it to y'all and ask, do you have any tips for students who are maybe looking to get into the field of instrumentation?
Yeah, I think you're right. It's not like the most obvious thing to get into. I didn't even know myself how I sort of pivoted into it was, I think most labs, usually just need someone to do the like grunt work, right? So just like, so maybe like Dr. Moore was mentioning earlier, you have to run a test overnight. And most people don't want to stay overnight and run a test. But like since I was in undergrad, that's what I did for like an entire summer pretty much. And so like that was my into the lab. And then once you're there, then you sort of you know the ins and outs of the lab, and then you make yourself useful in other ways. But I would say, even in the lab that I work in, there's always a need for people to just do small hands-on thing that maybe I don't have the time to do, or my advisor doesn't have time to do. But it's extremely, extremely valuable. We need someone to do it, and we're just limited by time. And so if we just literally have another person there who can do that, it is extremely valuable. And so I would sort of say, if you want to get into an instrumentation lab, I think we're always looking for people. I personally find that tons of people don't know that they're interested in that type of thing, and so we have a hard time finding people. But then once they're in there, they end up really enjoying the work. But it's hard to sort of to make a compelling argument for people to come in and stay super late overnight, or just operate the vacuum pumps, or just like watch this graph slowly decline on the screen. That's not so exciting. But I often find that whenever we do find people, they're even excited about that sort of thing once they actually get in the lab doing the hands-on work. So that's sort of what I would say is find a way to reach out to some people who are doing instrumentation, and I think more often than not they will have a need for you. Yeah, it's just about reaching out to them.
Yeah, basically, you always need help turning some screws, cleaning something up. That's always the case. So as Dr. Williams mentioned, volunteering is one way. I think it's best to be compensated for your time. In the beginning, you may have to volunteer, but after that, you should get compensated if you're an undergrad working in someone's lab. And it's actually the labs that I've been a part of, they're not just astronomy majors or physics majors. A lot of times there are engineers in there. So computer engineers, electrical engineers, mechanical engineers, aerospace engineers. And so there's a wide array of skill sets that could be useful depending on the type of lab that the student is trying to get into. And so basically, at the end of the day, you don't get anything if you don't ask. So go up to those people that are in that group and ask. It's easiest from my experience is to talk to the grad students and the postdocs first, and then they can put in a good word for you with the people that actually run the whole entire lab. And that's the best way, I think, to get started. Brittany, Dr. Miles, you probably have some additional suggestions.
Yeah, I think, well, one for maybe undergrads, I think you need someone who has time for you and is willing to do the mentorship. There are some groups that are like very procedure based, which can be rewarding for people if you want to get started up quickly. But if you want to learn more development, try to understand if you want to, I guess some groups are run like multi-level marketing schemes. And I just want you to make sure you get like time to actually understand why you're doing what you're doing, not just say, do this XYZ step and clock in and clock out. And then understand if you're motivated by the technology or more the science, because their professors differ on that regard too, even though the science is still important. So make sure you get what's fulfilling for you and a good mentor.
Excellent advice. Thank y'all.
If I can just
Yeah.
Just really quickly, yeah, I think you definitely what Dr. Miles just said. You don't want to get in a situation where you're just like turning screws and that's all you're doing. You definitely want to make sure that you're learning some other skills, or they're teaching science, or you're being actively mentored. That was like a situation that I was in. I'm happy to talk about that more, but you want to make sure that you're not just doing they're turning the screws. You want to make sure you're going up and yeah, all that good stuff.
Yeah, can I co-sign that also? It, in my opinion, it's on the student themselves to come forth and be upper front and say they want to do more. I've been at all these internships and in these different labs, and there are some students that kind of are complacent with being told to do specific tasks and aren't necessarily approaching the supervisors or the grad students or the postdocs saying that they want to do more. And don't let that be you. Like, please get up there, say, I want to learn this, this, and that, and the other. I want to have my own project that I can do on the side and still contribute to the team if the project doesn't directly translate to the deliverables that they need at that time. But yeah, please be like vocal and say what you need.
Excellent advice. Thank y'all. So we're gonna move to Q&A. So I've opened up all the questions that have been put in the Q&A box. So first we have Kayla. Oh, hello, friend, Kayla. Okay, so Kayla asked a question which is kind of like right along the lines of what we just talked about. Kayla asked, what are some ways to find schools or instrumentation projects for PhD? And I see also similarly, Caprice has a question kind of along this vein. Caprice asks, do you have any did you all have any formal classes in instrumentation? Because she's noticed that departments don't always have an instrumentation class. So either of these questions, did you all have formal classes in instrumentation? And then what are ways to find schools or instrumentation projects for PhDs?
I guess I'll talk to Kayla's question first. Yeah, I mean, so there are definitely some schools that or universities that specialize, or maybe not specialize, but have a strong emphasis on instrumentation. Off the top of my head, I know like UCLA, Santa Cruz, let's see, Johns Hopkins, a lot of the UT schools and the UT schools, so University of California, University of Texas schools, I know have like pretty strong emphasis on instrumentation. University of Arizona as well, Harvard, obviously. Yeah, there are a lot of schools that have strong emphasis on instrumentation. But the way that I would sort of recommend going, if maybe those are not schools that you are interested in, the way that I would recommend finding programs that are into instrumentation is sort of looking at what you typically do, looking at the research scientists and see what type of work they work on. They may not have a dedicated instrumentation page, but maybe there are a few faculty who work on instrumentation, and then reaching out to them and seeing what type of instrumentation projects they're working on at those universities. That's essentially pretty much what I did. At Carnegie, they didn't have a dedicated like instrumentation page, but I just found the 2 or 3 faculty who were actively working on instrumentation, or from their bios, it looked like they had worked on instrumentation in the past, and reached out to them to see if they were currently working on instrumentation and if they were looking for students. And then to Caprice's question, yeah, I mean, I didn't really have any formal classes in instrumentation. I majored in applied physics in undergrad, and so I had quite a bit of lab experience, but never had any like real like formal classes. I just sort of over time just picked up things. I'm definitely still learning a bunch now, even to this day. I definitely don't know, I think, all the things you need to know as a instrument builder. But I would say mostly, I've made it, I guess, this far, quote unquote, this far, without having any formal classes. I've just, been very deliberate in trying to pick up skills along the way and making sure things that I don't know, from the electronics point of view or from like a cryogenic systems point of view, making sure that the people who didn't know those things, I was being taught from them, basically, to sort of supplement whatever I didn't know.
Yeah, so I would say we didn't talk much about the funding model and how the money flows in and flows out, but that drives a lot of this. It's kind of a boom and bust cycle. if there's a large ground-based telescope or consortium that a university is a part of, there will be a stream of money that kind of flows in to support new instruments going on to those ground-based telescopes. If there is some type of particle detector, there's money typically for that. For satellites, it's literally boom and bust. There's a award, there's a bunch of money that flows in, many people are hired. And then after the 5 to 10 years of design, development, testing, and implementation, a lot of those people are actually laid off, and then they have to go find work somewhere else if they're at a university. Like research institutions like NASA are good at maintaining a lot of that technical staff. They just keep them there on other projects, but universities tend to struggle with maintaining that support system. With that being said, a student may see, there may be a big project going on at a university right now, and the students in high school, freshman, sophomore, so they say they want to go to this college. And then by the time they get to undergrad and applying for grad school, that project may be done. All the staff is let go. A lot of the engineering staff has been let go. The professors, the researchers, they're moving on to other projects that are data analysis based upon that previous satellite launch or instrument delivered to that ground-based telescope. The benefit with ground-based telescopes is you can kind of always go back and put on new instruments and do changes. But with satellites, once it's launched, it's up there, it is what it is. And that's the realm that I reside in. So some institutions that are pretty good for instrumentation that typically have a good flow of projects. So here, there's a few people here in Harvard Astronomy, but the Center for Astrophysics as a whole tends to have their hands in a lot of different things. So we always have opportunities. Down the road here, MIT, technology institution. So they're always going to have instrumentation-based projects going on. Caltech is similar. Cal Berkeley, University of Colorado Boulder, where I went to grad school, Penn State, University of Michigan, Ohio State's actually decent for this, Caprice. Trying to think, there's a few other places, but it's not a whole lot actually. Georgia Tech is one, but they're not as big in astronomy per se. In terms of courses, answering Caprice's question, at CU Boulder, we actually did have an instrumentation class, and it was taught by a professor named James Green, who was the principal investigator for the cosmic origin spectrograph on the Hubble Space Telescope. So that was a great opportunity. I took an electronics course in undergrad, but in terms of other graduate classes besides that instrumentation course, there was a data observation statistics course, but that was about it. A lot of it comes down to like an apprenticeship. You actually learn on the job for the most part with instrumentation compared to other subfields. And so going to an institution that has, again, a steady flow of funds for particular projects, that's really good. If you go there, you're almost guaranteed to have the opportunity to work on an instrumentation-based dissertation if you're talking about grad school. In terms of if the money dries up, then you're kind of SOL. So there are institutions that I thought about applying to for grad school where they had a lot of money when I was a junior and senior, and by the time I was a second or third year, the projects were basically done. So that's tough. But that's all that I had to say about that. It's really like looking before you apply a few years before, seeing if there's a new award. If there's a new award and they're going to get a lot of money for a new ground-based telescope, particle detector, or a satellite, then yeah, you definitely want to apply there. But if they're at the end and they're about to deliver, it's not likely there may be enough opportunity for you when you arrive.
Thank y'all for that. So actually kind of right along the lines of what you were kind of just saying when you were naming the institutions that are particularly good for this, John has a question. It's very impressive, the broad range of instruments that you're all working on. Does this kind of work require being at just a few institutions that have special resources and lots of staff, or can it happen at most colleges?
Yeah, I think that's a really good question. I think when I first started working on implementation, I would have been more inclined to say that it just happens at a few institutions. And that's, yeah, it's sort of like Dr. Moore was saying, it's just sort of where the money is. And who is getting the grants and winning the proposals, which I can talk at length that how biased that sort of system is. But sort of at the having gone through the system now, I'm actually more inclined to say that it's maybe not just a few institutions. I think that what I've been seeing a lot more of now is people repurposing a lot of like small telescopes and doing a lot more lab-based work. I'm seeing a lot of that in the past 2-3 years, and it's because you have a lot of people invest into these smaller telescopes or lab setups, and maybe they were for a few years they were whisked away by work that could be done on larger telescopes or and things like that. But you spend all this time investing into this equipment and these smaller telescopes, and a grad student or so comes along and says, "Hey, I want to repurpose this for something," or maybe a staff scientist says, "Hey, look, I've been meaning to repurpose this telescope or this detector for this use case. I just haven't had the time to do it myself. But if now you come along as a grad student or as a postbac or something like this and say, hey, I want to work on this, they would be more than happy to work with you. I actually know quite a few folks and who were in this exact situation, who there was a small detector that someone wanted to run or run some tests on or characterize. They just the scientists didn't have the time to do it, and so they came along and did a lot of that work. I think I'm sure Chris knows that at Harvard, I know Juliana, she repurposed this 1.3 meter telescope that had been in use for I think 5 to 10 years. And so I've been seeing a lot more things happening like that. And so so I would say it still definitely is the case that the institutions that have all the money that are winning all the grants are a few specialized institutions, and that's where you'll see most of the instrumentation work happening. But I think there are quite a lot of opportunities also at other institutions that have maybe not as many resources, but have some resources to dedicate to maybe some lab equipment or or to a small telescope that hasn't been used in a while. And so I guess it just comes down to a matter of reaching out to those people and finding those opportunities.
Yeah, I agree. I have nothing else to add on that. Well said.
I think this, I would say a lot of automated telescopes. I guess there are certain types of instrumentation where it would be significantly harder to set up and ask, do you have a clean room? Do you have a chamber to do radiative testing on like detectors and things like that? But I do think for decommissioning or not decommissioning, but automating telescopes, that's something maybe that can be done broadly and should be invested in. But I do think there needs to be more fellowships to allow people to stay at institutions for a while. Like a postdoc is about 2 to 3 years, and you spend one of those applying to jobs. I do think there should be more 5-year fellowships for instrumentation postdocs. Yeah.
Thank you.
And then I think I just wanted to say Kayla's questions about the PhDs. Definitely talk to the grad students to make sure you're not working with like a predator or someone who is traumatic to students, just so you have a good experience in grad school, because there are some people in instrumentation who are doing the most. So just make sure you get mentorship.
Thank you for bringing that up. That's such a key piece of advice. Thank you for that. So we have a couple questions that I would say fall under more sort of career, like networking type questions. So someone asks, do y'all find that conferences like AAS, so for those attending, that's American Astronomical Society, are good to network with other instrument scientists, or are conferences like SPIE, that's photonics and optics, more useful?
Yeah, I mean, I always thought that the for instrument scientists specifically, I think SPIE for me personally was a lot more useful. It's sort of like everyone's in the mode of talking about instruments anyway, And so it's very easy to, yeah, just like talk to people about instruments. I think at conferences at like AAS, you're more in the observation science mode. And so a lot of the instrument scientists, you know, in my experience, aren't even there anyway. Sometimes they're there, sometimes they're not. But usually at SPIE, since it happens, you know, every 2 years, pretty much all the instrument scientists will be out there. And so I always found it was better to network at. I've only been to one, to be fair, but I always found that it was better to network there and sort of see what people are working on at conferences like SPIE. And there should be. I wish there were more conferences like that, but from what I've seen, there typically isn't. And SPIE is the big one.
So I would say it depends on the objective of the person attending the conferences. So I made a statement earlier that astronomy is highly driven by observations. Now, with that being said, the new technology that's established or implemented in instrumentation is primarily driven by what the data analysis from the previous observations and what the theoreticians want to be observed. So for me personally, I've gone to about 5 or 6 AASs in my career and 4 SPIEs. I go to AAS, I have my own scientific interest, but I go there to listen to what the people who do the numerical simulations and data analysis, the recent discoveries, the recent findings, and seeing what are they missing? What parameter space is not being tapped yet? What new way we can observe something that uncover a new amount of information that wasn't there before. With that being said, you can take that information, put it in a proposal, and that is the science driver for a newer instrument or a new improvement in a component. I go to SPIE to, like Dr. Williams said, network, talk with people, see the newest technology, just have fun. For me, it's like being a kid in a candy store because it's very unique. At AAS, I mean, there are talks on instruments. They're mostly specific to certain science cases. At SPIE, you can just hear about new technology that people think is cool, that could go into an instrument at some point. With the SPIE, there are many different conferences. I think with the AAS, the question is more like the winter and the summer main AAS meetings, because there's these divisional meetings. So I'm talking in that regard. But for SPIE, there's optics and photonics, which happens every year in August in San Diego. But then there's also astronomical telescopes and space and instrumentation. And that's every 2 years. And that's like a pretty big conference for everything astronomical instrumentation, which I love to go to. If you're talking in terms of as an instrumentation grad student looking for a postdoc or a job opportunity, then go to SPIE if you had to choose one or the other. I would say if you're a beginning grad student just getting into instrumentation, go to AAS so you can see what the science needs are. Because eventually when you apply for your postdoc or your research position, if you choose to stay in academia after, you want to be at the forefront. You want to see where the science is going, what are the deficiencies in the current observations, and how can you construe a newer, better instrument to supersede the current suite.
You know, I'm curious. So I have not attended SPI in person, but I'm curious how has like your sense of belonging changed in instrumentation spaces? Because I know they're like AAS is pretty white, but I feel like SPI is whiter. And like sometimes it's like, dang, I got to put on the checkered shirt and the cargo shorts to fit in or something. Like, do you feel like you have to get co-signed by like someone more senior than yourself? How do you mentally prep yourself to kind of promote your idea, you know, and stuff like that?
So Dr. Williams, can I go first?
Oh, yeah, absolutely. Yeah.
All right. So Dr. Miles and Brittany, what are we talking about? So you said AAS seems kind of white to you. What kind of numbers are we talking about here?
I'm going to say 60%. I don't know.
I'll say more than that. But yeah, I mean,
60%
we're here
is
on the
low.
panel with Black people. So, you know, Black in Space Week, we're gonna be real with it to some extent. So I started going to AAS in 2014 after like my second year of PhD. and it was like 5 Black people. And you know, double S was like 3,000 in the winter. And I was like, where are the Black folks at? And I ran to another Black person. He's like, man, this is like the most I've seen in the past 3 years. I was like, what? There's only 5 of us. This is crazy. And now you guys know that the Benjamin Banneker group and other groups, you know, they brought in a lot of Black people. And so, you know, it's like 20, 30, 40 sometimes. And so to me, you know, Dr. Miles, right? I'm used to it being like 5. And so when it's 20 or 30, I'm like, hey, we coming up. Now it's got to be way better, right? We need much more. But yeah, I mean, SPIE, it's not going to be better in terms of the percentages. And I've been to SPIE since 2014. They're actually less in terms of percentage because it's more of a specialized skill set. Now in engineering, like I have a lot of engineer friends, NSBE, National Society of Black Engineers, you know, it's way more Black engineers and Black physicists and astronomers. But the interesting thing is, as I've gone higher and higher up in terms of further along in the career stage, I'm a researcher now, you know, just finished postdoc a couple of years ago. There's less and less of us. That's not a good thing. Basically, it's attrition. And people that are in instrumentation, and there's a question here talking about going to industry. A lot of us go to industry. And I actually don't blame most of us for doing that. But one of the main reasons I say it is I just really, really like stars. I really like instrumentation. But there are, if you have the skill set that we have, it's a very lucrative career outside of academia. So I don't fault anyone for making that leap. And then in terms of faculty or research staff positions, it's harder to get. If you can get one, you're way more secured in terms of less competition because of the skill set in terms of comparison to data analysis or theory folks. But the startup packages for instrumentalists are much larger than theory and data analysis people. So that's a barrier. And then, as you know, there's less of us due to attrition and people just going off into industry. So yeah, it's in terms of the numbers, we got a lot of work to do. If people got some ideas, I'm all ears for that.
Yeah, I don't have much to add. That was, yeah, very well said. I agree with pretty much everything you said.
But Dr. Williams, though, I'm Dr. Miles, sorry, and Dr. Williams. So we got SPIE next summer in Yokohama, Japan.
Yeah, we out. Yeah,
I'm gonna see both of y'all there, 2024.
Yeah. You'll see me out there. Yeah.
I'm planning on bringing 2 PhD students, a postdoc, and a couple other people on our team. So I want to see y'all there too. We can show up and show out.
Yeah.
Black folks in Japan.
Yeah, man.
I want to go to Japan. I don't work on no instruments. I want to go to Japan though.
Yeah, come
So I'm going to kind of combine the next 2 more career opportunity networking type questions. So Kayla asked, have any of you ever considered going into industry? And if so, what fields or types of positions did you consider? And then Caprice asks, specifically, have you all been able to find a community and network of Black instrumentation scientists very in line with what we're talking about right now? She's very curious about this.
Yeah, I mean, I've definitely considered going into industry. Yes, very much so like Dr. Moore was saying. Sort of by the time you finish your PhD, if you choose to do one, you sort of have a lot of skill sets that are very, very in demand. So it's definitely been a thought for me to go in industry. How I've sort of been planning my trajectory is I plan to stay in academia for as long as things keep going well. Sort of, if things, if I sort of see I'm not working on my own independent projects, if people are less interested in the things that I'm working on, I would sort of take that as a tip, okay, well, maybe I should start to make the transition into industry. That's just for me personally. Again, I really, really like instrumentation. I love exoplanets, working on atmospheres. But I'm not super tied to it. I would like to be, but it's quite hard to to know for certain where you're going to end up. And so being, sort of transitioning to industry, I think you have a lot more control over maybe the places where you'd like to end up, which is important for me. And so with regards to like what types of positions, interesting, I've been talking all this stuff about how I wouldn't want to be in software, but I think I've learned so much software over the years that like I think that's maybe a natural position for me to go into. So sort of like a software engineering role, and also just like but on the more technical hardware side, I could see myself maybe or I would look into maybe some like junior like mechanical engineering roles. I definitely don't have like a full mechanical engineering skill set, but I think I could like fill in as like a junior mechanical engineer and then sort of work my way up. Those are the positions I was looking at, or even maybe more into in a science role. So maybe somewhere at like NASA, working as like an instrument scientist, something like that. And I know NASA is not really like industry, but I don't consider it like hard like academia either. I'm sort of somewhere in between, I guess, like government. So like working in a government lab, something like that, would be or things that I would consider. And then to Caprice's question, a network of Black instrumentation scientists. I mean, yeah, I hope this is like at least for me the start of my community. I know I don't know too many. I know Greg Mosby at NASA Goddard. He's one of the only other like Black instrumentation people I know. But beyond that, to be honest, really, I don't know that. I mean, most of the other Black folk in astronomy I know sort of do science, and that's the community that I'm privy to. But with regards to instrumentation, not I know the community exists out there, and I hope this is the start of the instrumentation community for me. But I haven't quite been able to find that up until today, I guess. Yeah.
So we're talking about finding community and also was it 3 questions?
It was so finding a Black community of instrument scientists, and then whether you've ever considered an industry career, what position that was.
I got you. So I guess it helps a little bit that I'm also an observer. So the state of the field in terms of numbers of Black people is dire, but thankfully there are some. And every time I'm at a conference, I at least connect with somebody I know who's Black. And so I'm thankful for that. But I think maybe I could, tap into existing networks a little bit more to solidify, my instrumentation side a bit. And I think that's something I want to do in the next couple of years. And in terms of like whether I thought about leaving for industry, yes and no, because primarily, okay, I know I can get paid more, but I think in a sense, I feel like I've already made it financially. Like I don't have to struggle a lot right now. I know that's relatively speaking. I know some people, I know the goal is 6 figures for some people. That's not necessary. As long as I have my rent and I can play my games at the end of the day, I'm fine. But I think I want to stay in academia because after you get tenure, you have a lot of flexibility. So one thing I also like is interacting with students. You can teach what you want. You can make classes. Something I'm interested in is doing more like classes around Afrofuturism and how Black people, see themselves in technology, how they use it to express creativity and have agency and things like that. And I think you have more constraints on your time when you're in industry. I know you can make more, but I think there is a little bit more for me in terms of fulfillment. Yeah.
So have I thought about going into industry? Yes. Do I still get contacted about people in the industry? Yes. As of right now, I still really like stars. I really like the investigation aspect. I like working with my students and the researchers that I'm partnering with. So as of right now, I'm still in academia. There's one for everyone that's out there that's interested in What could they do in addition to academia if they obtained a PhD in astronomy instrumentation? These skill sets translate very well over to systems engineering and other subfields, because you get a big picture view of everything and you basically are kind of running the show to some extent. And that's highly applicable to many other projects in industry for systems engineering. In terms of a community for Black instrumentation scientists, great question, Caprice. It looks like we're gonna have to make that right here, right now. So myself, Brittany Miles, Jason Williams, Chris Moore, we're gonna grab Greg Mosby, grab whoever else wants to come along, and let's get this thing started then.
Well, we are right up at time. Thank y'all so much. I learned a ton. I hope our attendees did as well. Thank our incredible panelists. Thank you to our lovely interpreters. Y'all did not see me back here jumping screen to screen, figuring out who to give video access to, child, but we figured it out. Everybody's here. And this was awesome. Thank y'all so much.